Non, non, il y a... Rosine va introduire le sujet, donc t'inquiète pas. Tu ne peux pas apparaître tout de suite.
Tu me donnes le... C'est bon? Bon, bonjour à tous. Nous sommes réunis ici, enfin en personne ou bien connectés par le réseau, pour écouter une présentation par Elena Bellomi dans le cadre de sa candidature au grade de docteur en astronomie astrophysique de l'Université Paris-Sciences. Et le sujet que va nous présenter Elena, c'est la structure chimique en 3 dimensions du milieu interstellaire turbulent. Alors, vous avez, Elena, on prévoit environ, hein, c'est un tout petit peu flexible, 45 minutes de présentation. Ensuite, le jury posera des questions. Et puis, bien sûr, on se retirera ensuite pour délibérer. Alors, bon, bien évidemment, on aurait préféré des circonstances plus confortables et, disons, chaleureuses, un peu moins froides. Mais enfin, on espère que la turbulence va réchauffer et faire un processus de chauffage efficace. Voilà. Alors, quand vous êtes prêtes, nous vous écoutons et commençons.
Et ma présentation va être good afternoon, everybody. Today I'm going to talk about the 3D chemical structure of the local and diffuse ISM. So I'm going to introduce you for...
Pardon d'interrompre, on n'entend pas. Et on ne voit pas les slides non plus. Sur l'écran, je ne sais pas si vous comptez les projeter sur l'écran aussi.
Désolée, est-ce que vous m'entendez là?
Oui, c'est bien. D'accord.
Voilà. So sorry, I'm going to start again. And so today I'm going to talk to you about the 3D chemical structure of the local diffuse ISM. So I'm going to start with an introduction on what local diffuse and ISM means. Then I'm going to present you some observables that I've worked on. I'm going to present you how I modeled this local and diffuse ISM, and then how I compare the simulation with the observation, and then finally the results and the conclusions. So, what is the interstellar? So the ISM is the interstellar medium, which is the material, dust and gas, between the stars, in which the stars form by gravitational collapse in a cycle of matter. This cycle of matter starts with diffuse uniform clouds that then start to collapse and condensate into filaments and sheets, and finally gravitationally collapse, this core collapse, forming stars. This happens when the gravitational pull overcomes the pressure and the thermic and magnetic pressure. Then I'm gonna still go on, or okay. And then these stars undergo the thermal nuclear fusion, and they eject energy and matter in the interstellar medium. And when they die, they re-eject most of their mass, and this cycle. So this is here, it will be there, and then the cycle restarts. But star formation is a big riddle of today's astronomy, and to understand it, we need to understand the evolution of these clouds. And so, what's important to notice is that, can I change the slide? So this cycle is not only a dynamical cycle, but there's also a chemical evolution associated to it. And so the chemical species, as you can see in this graph, are actually tracers of the evolution, and they can bring us very valuable information on the physical conditions. In this cycle of matter, my work focuses on the first part, the diffuse clouds, because it's vital to understand the physics governing the division into phases and the formation of the first molecule. And so, what do we know about this diffuse ISM? We have a lot of information thanks to the variety of telescopes that can observe this interstellar medium at all wavelengths. We know that we have a richness, this observation shows a richness of features on the structure that it appears to be multi-scale, and then it's divided into different phases. So even in the neutral medium, this diffuse matter is divided in a colder and denser called Soutenance, so closed neutral medium, and it coexists and it's in thermal pressure, almost at thermal pressure, with a warmer phase that is then hotter and more diffuse. From the chemical point of view, we observe both ions and molecules in the...
Tu n'es pas en partage d'écran. Screen sharing.
Sorry for the interruption.
Non, c'est partage d'écran. Le duplicata, c'est bien.
Ah non, ok.
C'est sur le Zoom.
Can you see now?
Maintenant, on voit ton écran.
Yeah. Technical difficulties and we prepare. So from the chemical point of view, we can observe. We see both ions and molecules, and different chemical species are correlated. And this medium is also highly dynamical, and there are different energy reservoirs and sources like cosmic rays, photon, magnetic fields, and turbulence that appear to be in equipartition, meaning that when we want to understand this medium, we can't, there's no one energy source that prevails on the other or can be neglected compared to the others. And all these properties are global. So when we observe in different directions, this is the medium that we observe. And so all this complexity shown by the observation needs a counterpart, a theoretical effort to try to explain it. So if you want to understand, but okay, I need to say one more thing. It is that it's virtually impossible to do the 3D time evolution, the chemical time evolution. So these efforts, when we want to understand the structure of the matter, people use dynamical simulation, which are 3D time dependent. And but there are no chemical content in it. And when we want to access the chemical properties, so to explain the abundance of ions and molecules, people use chemical models, but they are uncorrelated from the structure. And the structure is important also for the chemistry because usually the main ingredients of these chemical models are photons because they can distract molecules. And the photons, the propagation of photons is actually affected by the structure. And so in the past, there have been efforts to try to combine these two that are clearly coupled in the reality, in the physics of the ISM. There's some efforts try to put ad hoc dynamical parameter into the chemistry, and some other use this dynamical simulation by solving in it a small chemical network. And it's in this direction that my work inscribed. So during this PhD, I used on one side these models, so this simulation, dynamical simulation with a small chemical network, and then I post-treated them chemically to have the abundance of more species. And on the other side, I used observations. And so let's see how I choose these observations. So first, the hydrogen, because hydrogen is the most abundant element in the ISM, and it composes up to 70% of the mass. And so it gives us information on the structure, the division into phases, and the morphology in general of the ISM. And it's in its molecular form, so H2, molecular hydrogen, is the most abundant molecule. And this molecule is precursor of the rest of the chemistry. So basically, it's the first one. It's when H2 form, it's the first transition from atomic to molecular. And so thanks to H2, we can characterize the molecular contents. The other species that I'm going to talk about in this talk is CH+, because thanks to its chemical properties, is actually often a mystery of the ISM, and many models have problem producing it, the right amount. And so we were up for the challenge. We tried to be up for the challenge. And then there's a third species that I taught in my manuscript that I'm not going to present today, which is the natural carbon, which is a proxy for pressure. So let's start with H2. So here I show a plot in which we have the column density of H2 in the y-axis as a function of the total column density. And these observations of H2 are done in absorption in UV. So it basically means that for each point of this graph, we have the information of the total amount of matter in the lines of sight and the abundance in the column density of H2. And we can notice, first of all, that all the points are between these two dashed lines, the fully molecular and the unshaded warm gas, which means that every lines of sight intersect different clouds and different phases. Then we can notice that as we increase the column density, the fraction of H2 increases. The fraction of H2 is this solid line in the different colored color regions. And we can see that at column density of 3 × 10⁻20 centimeters minus 2, we have a transition. So from mainly atomic, it becomes more molecular. Okay, we can also notice that as the fraction of H2 increases, so when the column density increases, when we go to the right, the dispersion of this fraction decreases. So basically, these regions become slender and slender. And so since H is so important, H and H2, as I said before, there are many theoretical efforts that focused on it. And usually they are very good at reproducing each one of these lines of sight. But here, oppositely to what they do, we want to understand all these lines of sight kind of at once. So the shape as a whole. So where the transition is, why it's there, why it's so thick, etc. If we now go to the second observable, the second observable is CH+. So here again, I plot the column density of CH+ in the y-axis as a function of the total column density. And we can see that at low column density, we mostly have upper limits, which are these green points. And the number of upper limits decreases when the column density increases. And at high column density, we have only detection. And we can also notice that the dispersion of the points is very large. So what did the theoretical effort say on this abundance? So as I said before, many models try to reproduce it, but some of them, the one that didn't include any dynamically, fail. So here I show you a model so this is the results of the model, these black lines, and these are the observational points. And we can see that there is a discrepancy of order of magnitude. And so to reconcile the prediction with the observation, different scenarios have been invoked. Here I show you an example in the bottom panel. And so this is a chemical code that investigates the dissipation of turbulence. And we can see that it's better at reproducing it. And what we need to notice is that every one of these colored lines, it's a set of different parameters. So to explain the distribution of points, to explain the dispersion, we need different parameters. And so these two observables bring us to an ensemble of questions that we try to answer. So what is where does this dispersion of points in the observation come from? Is it something physical? What can we deduce from it? And how does the turbulence, the external radiation field, the magnetic field affect this distribution of points? So what are the physical properties that controls these observables? And so to tackle the problem, I did an extensive parameter study, so to disentangle these physical properties. And I ran numerical simulations that have been post-processed chemically to access the 3D chemical content. And then I'm going to explain to you also the new tool that I created to effectively compare the results from this simulation to the observation. So since the problem is highly nonlinear, there are no analytical solutions. And since we are in conditions of density that are more vacuum than the vacuum that we can create on Earth, we can't do lab experiments. So the only experiments that we can do, that we can conduct, are numerical experiments. So we did such experiment with Ramses, which is a grid-based solver with adaptive mesh refinement that solves MHD equation with also including gravity. Gravity is both self-gravity and the action of stars in dark matter. And the matter of the diffuse medium in the solar neighborhood is simulated over a box of size L with periodic boundary condition. And it's isotopically illuminated by all sides by OB stars, which are sources of UV photons. A turbulence forcing in Fourier space is done to mimic the injection at large scales. And Ramses computes the abundance of H2 taken into account its transport and also its formation and destruction, accounting for the effective radiation field, so computing a radiative transport. And then a key ingredient are the microphysical processes, so the heating and the cooling. We included photoelectric effect and cosmic ray heating, and cooling from line emission due subsequent to collision. And if we wonder in which physical condition we have thermal equilibrium, so where the heating is equal to the cooling, we can plot it on this diagram that shows the pressure as a function of density. And the black line indicates for which pressure and density we have heating equal cooling. And we can immediately notice that this curve is not monotonic, but between the pressure, peak rate, and P minimal, we have three different branches, two of which are stable and are at the density and temperature. So yes, this dotted line are the temperatures. And so they are at density and temperatures that correspond to the phases that we observe. So WNM and CNM. And why do I say that they are stable? It's because if we perturb the gas, it enters either a heating region or a cooling region that push it back on that curve. While when we are in the other part of the branch, so the central one, a little perturbation makes the gas entering in a cooling or a heating region that pushes far from the gas. And so for this graph, basically what we can see is that the division into phases is a natural reaction of the gas to this heating and cooling. So it's very important to include it. And so with for each one, so with a set of parameters, we can run a Ramses simulation. Since we are interested in doing a parametric study, here I show you the different parameters and their ranges. And each one of these parameters is linked to a physical ingredient of the ISM. For instance, the size of the box is the illumination scale, so the distance at which these OB stars are located. The mean density indicates the mass in the ISM. The external radiation field indicates the density of this OB star. And here I show you in green the reference value, so what I'm gonna call later the fiducial simulation. So if we look at an output of Ramses, Ramses informs on physical condition in each cell of our box. So in each cell, we have the temperature, the density, the extinction, which is the absorption of photons, the velocity and the magnetic field. We have the mean molecular density because it computes the density of H2. And we have the self-shielding of H2 because H2 absorbs in lines and so it deprives the medium of photon that can dissociate it. So basically it shadows. And here on the right, I show you a cut of the temperature and on the density. And first of all, with the arrows or the velocity. And first of all, you can notice that the denser parts are actually the cooler. So we can see the phases. And from the box containing the density and the box containing the temperature, we can do a probability histogram. A 2D probability histogram that I show here on the left. So again, the diagonal lines are the isotherms, and the color codes indicate the fraction of mass in each condition of pressure and density. Here I show again the equilibrium curve line, and this horizontal line is the mean pressure of this simulation. We can see that the points are not on the curve, but are actually dispersed. There is a range of pressure in which they are. And this is due to turbulence that kicks the gas out of the equilibrium curve. If you now imagine to have more heating, this curve will be displaced to the upside. It will go up, okay? And so it would lead to an increased pressure in which the density of CNM is higher. And I'm telling you this because it's going to be important later. So now that we have the cubes with all the physical quantities coming from Ramses, we can process it chemically and find the abundance at equilibrium of 151 species. This chemical solver can be used with two different prescriptions. One that does everything the 151 species at equilibrium, and another that takes the abundance of the out of equilibrium H2 coming from Ramses. So this chemical solver is important to give us the chemical composition of the diffuse ISM. And this prescription will allow us later to estimate the impact of the out of equilibrium H2 on the chemistry. So from this post-Cossack cube with the density of the different chemicals, the different species, we can integrate along one line of sight and compute the column density. But this is not the column density that we are going to compare to the observations, because these are from cube of 200 parsec. And it's important to take into account the distribution. So how far are these stars? But the amount of diffuse matter that that is intercepted by these lines of sight doesn't necessarily correspond to the distance of the star, because we know that the amount of matter in our galaxy is decreasing exponentially as we go farther from the midplane. I should tell you that before I forgot, we know that we are testing the local medium because we have excluded all the other galaxy at high redshift or material associated to extragalactic clouds. And so once we have the distances and their position in the sky, we can compute the length of the lines of sight, so the length of this diffuse gas that we have intercepted. And from this distribution, we can create the same distribution for our simulation using one box as a building blocks and putting one box behind the other until we reach the length desired. We also need to take into account that what we are simulating is the neutral medium, and there actually a part of each, there's a percentage in each lines of sight that is composed of a ionized medium. So we need to take into account a filling factor that here we assume to be 0.5. And so let's take the example of H2. This is an 8-off projection of the observation of the background stars where we observe, against which we observe H2, well, H2 was observed. So we can see, so this is in galactic coordinates, and the color codes indicates the distance from the stars. Then with this simplification of having the disk, having the disk of 200 parsec, we can compute the distribution of length that we can see here in this histogram, where the color code is the same as before for detection and not limits. And so from our column density, so the top right of a box of 200 parsec, we can again do a probability histogram of the column density of H2 as a function of the total column density. And these these dotted lines are is a fraction of H2. But all the stars are not at 200 parsec. We can see from these histograms that the length of the lines of sight go from 100 parsec to 3 kiloparsec. So when we take into account this distribution, we obtain this probability histogram that is called Kingfisher diagram. And where each, the color codes indicate the fraction of lines of sight in each beam, okay? And so we can see that the effect of the reconstruction actually enhance the bimodality. And so let's dive in our Kingfisher diagram and let's compare it to the observations. So on the left, we have the observation, on the right, the simulation. We can see, so again, the column density of H2 as a function of the total column density, and we can see that both simulated and observed points are always a mixture of different phases and different clouds, and that they have the same general trend. If we now try to superpose them, we can see that the peak in the probability histogram, so where the probability histogram is the redder, coincide where we have the matches, the bulk of the detection. But now, how to compare this quantitatively? We could, for instance, divide the graph as I showed you before, count the observations, the fraction of observation in each quadrant, count the fraction of simulation in each quadrant, and then how to weight the different quadrants. So there are like, we decide to do a different approach, which is based on this one, and we used a KS test, a modified version of the KS test. So I'm just going to remind you very quickly what the KS test is. The KS test is a 1D cumulative test that compares two PDFs. And basically it looks for the maximum value of the absolute distance between the two distributions. But what we have is a distribution in 2D, right? The total column density and the column density of H2. And the cumulative probability distribution is not well defined in dimension higher than 1. And so I followed Peacock's idea, and instead of this cumulative probability, I used an integrated probability, so basically the fraction of points. So the basic idea is to divide the diagram in 4 different quadrants, taking each observation as the origin of these different quadrants. And like this, we have a fraction of observation and simulation in each quadrant. And what this modified KS test look for is the maximum ratio between the two. So where the two are the most different, for which point and which quadrants. And here for the fiducial simulation, the observational points that maximizes this distance is this star, and the region is this gray region. And we can see that the KS test, the KS distance is around 1, which means that is in this particular region, we have 10 times more observation than simulation, but in all the other quadrants, also divided using the other observable points, we have a better ratio. So this is the word ratio. And the fact that we don't only have the points that maximizes, but also the quadrant gives us physical insight. Because here, for instance, we know that the dispersions of points in the observation, it's larger than the one that we are simulating. So with all this, let's go to some physical results. So let's start with the numerical parameter, the numerical resolution. So if here I simulated a box of 64, which means that in each direction of the cube, we have 64 cells. So basically every cell has a size of 3 parsec. And on the right, it's for a resolution of 512. So each cell is 0.4 parsec. Okay, so the fact that these two, this Kingfisher diagram, so this probability histogram, is independent from the resolutions, allows us to do a parametric study at a lower resolution, a more moderate resolution of 256, But also it gives us physical insight, because it means that the cold and dense structures that are created between 0.4 and 3 parsec do not affect the column density of H2, indicating that the column density of H2 is actually built up in structure larger than 3 parsec. If we now look at two different parameters, so I remind you that the mean density is proxy for the mass, it's parameterize the mass, and the external radiation field parameterize the OB density. We can see that these two parameters affect greatly the Kingfisher diagram. So notice that the axes are in log scales. So even if sometimes it seems a small displacement, it can be like 1 order of magnitude, okay? And the red simulation is the fiducial simulation. So here, if I go on the right, it means that I'm increasing the external radiation field. And if I go up, it means I'm decreasing the mean density. And we can see that the effects are similar, meaning that the molecular fraction is decreasing, but its dispersion is increasing, and the transition is shifted to the right towards larger column densities. So let's focus on just this example, because otherwise it's too crowded. So if I go up again, I decrease the mean density. If I go to the right, I increase the radiation field. And we can, so if you remember, as I said before, when we increase the radiation field, we are increasing the heating, and the mean pressure increases, leading to a denser CNM. But since the mean density is fixed, the fraction of CNM decreases, and so naturally the fraction of H2 decreases. And this also favors occurrence of lines of sight with lower fraction, so we can see that these parts of the graph become redder. Another effect of the external radiation field and the mean density is that it's decreasing the shielding. And so decreasing the shielding has the effect that we need higher density to produce high molecular clouds. And so the transition is shifted toward higher column density. And what I said before, these have opposite effects, but if you look at them, they are not symmetrical. And it is because even when I have a high radiation field, this doesn't preclude the existence of clouds with a high fraction of H2, even if it does reduce the probability. And if we now look this as scarce distances, we can see that the fact that this Kingfish diagram changed a lot with these two parameters is seen in this graph, where we have like a big excursion of differences. So I reminded you that when the chaos distance is big, it means that the simulation are different from the observation. And when it's low, it means that they are similar. Okay. And so now let's look very fast, I guess, to another another parameter, sorry, which is the size of the box, which is the illumination scale, so the distances of this OB star. Before we had 200 parsec, which is this graph here. If we touch the quantity, sorry, if we touch these illumination scales, we are also affecting the quantity of matter in our box, and so the shielding of UV photon. So when we decrease the size of this box, we naturally decrease the fraction of H2, as you can see in this graph. But also, since the turbulence forcing is mainly driven at a size that is proportional to the size of the box, the fact that we are decreasing the box, it means that we are decreasing the size of the density fluctuation. But since the length of lines of sight that we are creating are the same, because they are dictated by the observation, we are actually putting more of this density fluctuation in the lines of sight, which has the effect of squeezing this diagram in two directions. Now here I have effect of other parameters that I'm probably going to skip. And so the conclusion on the H-H2 transition, we have seen that it's a tracer of some physical parameters, because it's greatly affected by them. which are this mean density, the external radiation field, and the size of the box. And why it's so much affected by them is because these parameters are the one regulating the mean pressure, and so the fraction in the different phases. And they also control the size of these different fluctuations. The best concordance of the simulation with the observation is found for values that are in agreement with the observation in the solar neighborhood. And the column density of H2 are built up in structure larger than 3 and smaller than 10. If we now go to CH+, CH+ has particular properties because its formation is, its destruction is very fast. And so the only reaction, the only formation reaction that can compete with it is an endothermic reaction that I show here. That's basically the fact that it is endothermic, it means that it needs high temperatures. And the fact, and one of the reactants is H2. So to form it, we imagine that we need lots of H2 and a high temperature. The fact that it is rapidly destructed, it means that it's short-lived. So it's going to be observed where it's formed. And I remind you also that the models that do not include dynamics are underestimated systematically. So if we now look for the fiducial simulation, what we obtain is column density of CH+ as function of the total column density. We obtain this graph, where again the color codes indicate the fraction of lines of sight for a certain density and total column density and column density of CH+. And we can notice that the bulk of the distribution corresponds not only to the total column density of the observation, but also to the right amount, to the right fraction of CH+. These different lines indicate the isofractions. And we can see that where we have, so the distribution is bimodal, and the peak at low column density is actually in correspondence of all these non-detection upper limits. And so now we can wonder, where does this CH come from? And so let's look in which condition of pressure and density is formed. So here I do again a probability histogram of the is a function of the pressure as a function of the density, weighted by CH+. So basically, the color codes indicates the fraction of CH+. And we can see that most of CH+ is actually produced between 8,000 Kelvin and 500 Kelvin. And it is in this out of equilibrium gas, and that a certain fraction is produced also in the CNM, where H2 is abundant. But so, out of equilibrium gas, so is it due to out of equilibrium H2? I remind you that we can compute the whole chemistry at equilibrium to see the effect of the out of equilibrium too. And when we compute the whole chemistry at equilibrium, so also H2, the fraction of CH+ is underestimated by 2 orders of magnitudes. And what has changed is the production of CH+ in this out of equilibrium phase. And so this shows us that this out of equilibrium to this warm H2 is actually necessary and to boosting the production of CH+ by at least 2 orders of magnitudes in this simulation. And where does this out of equilibrium H2 come from? Is actually H2 that is forming the CNM, and it is advected in warmer phases by turbulence. So we expect turbulence to be having a major impact on this graph. And so turbulence turbulence is injected in our simulation as with 2 different parameters. One, which is the acceleration parameter in the momentum conservation equation. And the other ones are the modes. So we can play on both these parameters. And so in this graph, I show you, if you go to the right, you're increasing the forcing. And if you are going up, you are increasing the percentage in solenoidal modes. And so here we can see that since the turbulence increases the pressure and the pressure variation, it decreases the fraction of H2 and increases the out of equilibrium phase. And this pressure variation give broader column density, but the effect is less visible in solenoidal modes because solenoidal modes prevent the gas from condensating back to the CNM. So we have it underestimates H2, and so it affects CH+. So to summarize on this CH+, it's the parameters that greatly affect H2 also greatly affect CH+. And moreover, it seems to be a tracer of turbulence. And this turbulent transport of this large-scale turbulence can be a viable scenario to explain the abundances of CH+. We have the Titan's concordance from for the same parameters with the same parameters as before, and we have seen that H2 is a key ingredient, especially warm H2. So in the manuscript, I explain how I did a code for the excitation of H2. And so one of the improvements will be to take into account the excitation of H2 in the formation of CH+, because this internal excitation can lower the gap in the formation of CH+. And so to summarize, here I explain you part of my work in which, since we wanted to understand the effects of the different physical parameters, we did a large parametric study with the chemical post-process, and this large parametric study has been done with state-of-the-art simulation that not only include the multi-phase medium, but also the formation and destruction of H2. And then I developed new tools to compare the results of our simulation to the observations. And so from the physical point of view, we have seen that taking into account the distance of each one of the background sources is actually necessary to explain the range of observed column density, and especially their statistics. And that in the end, this large dispersion of lines of sight can be reproduced by the joint action of the turbulence and the thermal instability. We could reproduce well the abundances of CH+ and the transition from atomic to molecular hydrogen without even invoking different parameters along the lines of sight. And so now we see the observations as local condition, but also their probabilistic ordering along the lines of sight. Here I didn't talk about C1 population, but I also did a code to compute the excitation of C1 in its fine structure. And fortunately, the joint action of the turbulence and the thermal instability cannot explain the observations. And so finally, so this was the first step in a study where we see the observations as tracers of some physics in which the physical conditions are encoded. And so not only the observation can give us some constraints on the simulation, but also the simulation can give us great insights and understanding better the observations. And so here I studied 3 different observables, but this study should be extending to as many possible atomic and molecular traces. As I said before, we should include the excitation of H2 in the chemical solver. So this is the close next step. And then what is interesting with this version of the cast distance is that can be done in whatever dimension. Just the quadrants will become cube or hypercube. So it can be done on more observable at the same time. Thank you. No.
Thank you very much, Elena. Merci, Elena. Et d'être dans les temps, très bien. Même un tout petit peu.
Même moins.
Une minute de moins. Alors, on va commencer la session de questions. Alors, moi, je propose, à moins que vous soyez d'autres préférences, de commencer par les rapporteurs. Donc, là, Cécile, tu veux démarrer? Tu es d'accord?
Oui, oui, je suis d'accord.
Ah, on te voit là, très bien.
C'est bon? Vous m'entendez?
Et très bien aussi, oui.
Okay. So, first I want to congratulate Elena for the work that you have presented, both for your manuscript that I have found very impressive, and also for your presentation, which was very concise, clear, and entertaining. So, as I write in my report, I've been impressed by the depth and the precision with which you've introduced all the aspects of the diffuse medium, with which you have discussed all the physical process and described all the tools you've used. So thank you for inviting me to the jury of your thesis, because as an observer, and in particular an observer of the diffuse interstellar medium with the help of the absorption line, I've been very interested to read about the method developed in your thesis, which produces at the same time simulations and statistical analysis of the observations. So I think this analysis method is very promising, and you need only consider the richness of the conclusions that you have drawn by discussing the impact of the various parameters. And I think it's very remarkable how well you represent the H1 to H2 transitions and the CH plus abundance. That's very impressive. So actually, I didn't know that you were not going to speak about the carbon one, and I wanted to start with a few questions about carbon one. Is that okay for you?
Yeah, sure. Yeah.
So, I think it's very interesting that you show that the introduction of turbulence does not create any compression, very large compression zones. And actually, I knew that Edward Jenkins and Todd Tripp were extending their study of galactic carbon 1 by observing extragalactic lines of sight to avoid contamination by the environment of the target stars. So a few days ago, I asked Ed Jenkins what were their results, and he told me that most of the time the high pressure component is absent from the extragalactic targets. So he therefore thinks that the probability that probably the high pressure component arises from the immediate environment of the target star. This is one of the explanation that you had put forward in your manuscript. So maybe I recommend that you talked with Ed Jenkins. I think it would be interesting for you. So maybe actually the low end of the pressure distribution may be therefore more interesting than the overpressured gas. And I have a question on that. It's interesting to see in your histograms of pressures versus NH, this is your slide 21, I think, that there seems to be a fair amount of gas at pressures below the minimum for a static gas that is influenced by the thermal instability. That minimum is slightly above 10 to the third, following Wolfire et al. 2003. And also, yeah, so yeah, on this, you can see that there is a fair amount of gas, which is it's still red below 3. And also in your probability C1 probability histograms of F2 versus F1, we can see that the regions where both F1 and F2 approach 0, the lowest points for F1 and F2, which are the lowest pressure points, I think, They indicate also that these regions are dark red in your plots, so they indicate also that there is a lot of under-pressured gas, even maybe more than what is appearing here. So I just wanted to hear a little bit more from you about these rarefactions. How do you explain them? Are they due just to the presence of gas out of equilibrium? Do you know the pressure distribution functions? So what is the relative proportions of the low pressure regions?
Okay. So thank you for accepting. So if you go in order, thank you for accepting being my referee, one of my referee. And second, yeah, I think I should need to talk to Jenkins. And so third, to go to the pressure. So if we start on this graph, these red points here. So what I need to say is that there is not one equilibrium curve, right? Because in my gas, what I take into account is the effective radiation field, because that's what hit in the gas in each point of the simulation. So when I go more inside of the simulation, there are actually an effective radiation field that is different. And so I showed it a little bit here, where, for instance, I show two different curves. This one is extreme because we don't have that kind of extinction, but it's just to show that as we go inside the gas, actually it follows all the other lines. And for what concerns, so this graph, yeah, we have the bulk of the points in the probability histogram that is also at very low pressure, very low ratio of H2 and F1. But this is actually, so it can be, when I am at a lower resolution, there is probably too much diffusion of the code. And so we are kind of increasing the out of equilibrium curve, the out of equilibrium gas artificially. So it's something that it needs to be taken into account, and we can see that we haven't still converged. So this explains why here, for instance, we don't have any higher ratio of H2 and F1, because we are not creating these denser clumps in which, first of all, C1 is formed, because so C1, so first of all, we need to have C1, right? So C plus needs to have transition to C1, and in our simulation, we see it in the inside shell of CNM. And once we have this, it needs to be in clouds that either are denser or they are bigger. And so sometimes we don't have those, so we don't have enough C1. And when we go to very high, I didn't put it here, we can see, like, yeah, even here, we can see that when we create a lot of C1, still what we are creating is like regions that are too cold to have high pressure, because even if the density is high, we don't have that enough temperature. I don't know if I have answered all your questions.
Yeah, okay, thank you. So actually, I am wondering also on the amount of C1 in the WNM. You have shown in one of the figures, which you didn't show now, but you showed in your manuscript. You showed the column density of C1 as a function of velocity, and then on two of the three plots, I can see components that obviously belongs to the WNM because they are wide, they are broad, they are warm. But for example, if you take the figure 1 from Jenkins in 2011, they show there the neutral carbon fraction is less than 10 to the minus 4 for the warm medium. So their conclusion is the WNM is virtually invisible in our survey of C1. But apparently we do see C1 and also I must say that also traditionally in the observations, we see much more C1 very, very narrow from cold gas than from the warm gas. I think I've never seen C1. So how much, what is the proportion of C1 that you see in the WNM?
So I don't think I have a graph here. I think that we yeah, that's a very good point. Like in the end, since observation has a certain sensitivity, even if WNM occupies a lot of the volume, so even the graph that they show in the manuscripts, they are weighted by the fraction of C, sorry, but still it's more abundant in CNM than WNM because we have more mass of C1 in the CNM, and so I think I wouldn't expect like this if we just do it without taking into account the sensitivity of the instrument, etc. It wouldn't make that much sense to compare directly this histogram to the observation, because for sure we are going to have like the bulk of our simulation in fraction of F2 and F1 that wouldn't even be observed by the observations. And then there was something else I wanted to say. I said I think it was like how much. So C effectively we have like in two regions. I have memory in our PN diagram, and there is a lot. The most of the mass come from CNM, and there's actually a part in the out of equilibrium part of the graph, which corresponds is actually due to it's a consequence of CH plus, because it's the destruction is the pulse of the graph in which is the physical condition. Sorry, is the physical condition in which CH plus is destroyed by photons and by electrons, because it's also the sum of electrons, and so raising C. But even in our simulation, the fraction is coming from because it's in the warmer gas, it's mainly C plus more than C in this out of equilibrium gas.
Okay, thank you. Can I ask a question? I am confused about what you called the turbulent velocity dispersion of the gas. What you call the broadening parameter at large, the broadening parameter at large scale, I think, and you take B equals 8. I'm confused about that because in the absorption lines of H2, CH plus, C1, the B value is something like from 2 to 4 kilometers per second. It's never as large as 8. So, so I am a bit confused about this low broadening parameter, what you call the broadening parameter large scale, what we observe in the absorption lines, and also what you call the microturbulence. Can you explain the choice of B equals 8 and how it relates to what we observe?
Yes. So the broadening parameter that I'm talking as a parameter there is this volume here that affects the self-shielding of H2. Yeah. So that was a choice. So we explore also other values like B equal 1, B equal 2. That was a choice because in our simulation, we just have, it's not done coherently. So there's just one Doppler broadening, because otherwise it would be like too computationally expensive to include it in each part of the hydrogens constant. So what I call there as a parameter, the Doppler parameter is this one, and it affects the shielding of H2. So the choice was done because we didn't want to overestimate. We didn't want to we didn't want to fake. I don't know how to say it without getting confused with under and over. It's it was a choice so that our shielding was a large scale one, basically. Because so this broader parameter like microturbulence, etc., it's going to depend on which scales I'm looking at, right? And so since when I'm inside the clouds, I'm looking until the border of the clouds, the scales that I'm considering are large. So we can have like a mixing of different broader parameters, which has in the end it will affect the H2 as if it was a large Doppler. And so this was clearly a choice for preventing the overestimation of H2 at large scales. Then for what concerns transition of A and H2, and the results show that B equal 2 and B equal 8 give similar results. So it didn't affect our Kingfisher diagram. But it could be important for all the species that are not created inside the clouds, but on the outer part. So for instance, CH+, I think I have a graph here. And because having such a large Doppler broadening actually can underestimate in the small scale the abundance of H2. And so here I should have it. So this is the effect of the Doppler broadening on CH+. And we can see that actually it affects a lot the CH+, which is formed in, I don't know if I have a picture to show you where CH+ is formed. Yeah, it's formed here. So inside, you can imagine this is a cut. You can imagine that we have H2. And so it's formed in the outer shell because it's when H2 becomes warmer because it's kicked out by the turbulence. And so this is something that we are currently studying, the effects of other parameters like the B2 on, but it doesn't affect H2. And the other question was like, so what I call microturbulence. Usually microturbulence then for me is not this large scale broadening that can affect the shielding. But it's, for instance, the microturbulence in one concept. So for one concept, we usually take 1 kilometer per second. So yeah, there are kind of two different parameters.
Okay, so do I understand correctly that to relate this B that you use, the velocity dispersion at large scale, to the B value that we see in the individual velocity component that we observe in the spectra, is it conceivable that your B accounts for the presence in the spectra of several distinct absorption?
Exactly. Yeah, exactly. All the
individual B. So each of them have an individual B of 2, and they are separated by 2 or 3 kilometers, and in total that makes 8, right?
Exactly. That's exactly.
And the B is over a length of 200 parsec. This is on one box, or this is on?
It's, well, usually it's like maximum half a box, right? Because the maximum you can get the center, which is the farther point. But again, it's like the same one for the whole box. So also when we are on the side, we still keep that one. That's why it's a mean, because otherwise if it was like on hand parsec, we can even imagine on putting a larger parameter.
Okay, and maybe I ask a last question, which is on kinematics again, following on this subject. I understand that your focus was not kinematics at all, but you have. I know that you have the kinematic information because you have shown it in the plot I referred to for C1. So I find very interesting the possibility to study how the gas is kinematically distributed in a sightline under the effect of introducing the large-scale turbulence. And especially the possibility to study this in connection with the spatial information, because in your simulations you have both the kinematics and the spatial information, which we don't have it from the spectra. We only in the spectra the different units of gas are only differentiated by their velocity only. So I think this would be very interesting to study this. And for example, I would be interested to see if turbulence creates velocity components embedded in gas with a different velocity. Or I guess you find CNM embedded in WNM gas. I think it would be interesting to see how their respective velocities relate to one another. So my question is just, do you know if this kind of study has been done with your simulations, or do you think it would be interesting to do that?
I think it would be interesting, and I think it's feasible because we clearly have the information of the velocity fields in every direction in every cell. Then it's going to depend like. I think it's feasible, and it would be like very, very interesting. Yeah, I didn't focus that much on the dynamic, just not to go crazy on the turbulence. We check the dispersion that we were having at different scales. It would be very interesting to see how they move and their speeds from the inside. Yeah.
Okay. Well, thank you very much.
Thank you.
Pierre,
Oui, bonjour, bonjour Elena.
Bonjour.
Vous m'entendez, ça va?
Yes.
Ok. Bon, eh bien, merci pour la présentation. Malgré la distance, c'était très agréable et pas facile. Et merci pour le manuscrit qui est très. Sorry, in English, no?
Yeah.
Yes.
Yes.
Sorry.
Yeah, you can comment in French and then
yeah. Okay.
2 questions, no problem.
Okay, so yes, so the manuscript is very nice with very beautiful illustrations and a lot of figures which make it easy to read. Well, as you know, I have some questions about numbers, which I found. Well, I like numbers, you could say. I think so. So I ask a question. Actually, I have a lot of questions, but I will pick up a few ones, some which are maybe a little bit technical, but I would like to understand. There are things that I didn't understand. It's me. And then I have some perspective questions on your work. So there is something I would like you to explain me again. I think it was on the page 40 in your slides. And so I'm sorry because I didn't understand really the links of cause and effects between increasing G naught and the decrease of FCNM. So just to be clear here, FCNM is the fraction of mass of the CNM,
yes.
Right? So can you again explain me how it works?
Yes. Can I go on the blackboard? Coming. I can even choose the colors. So I'm gonna. It's coming. It's starting plot it and then. Perfect. Can you see it?
Yeah. Okay. Okay.
So if this is our pressure, and this is the density, I have an equilibrium curve like this, right? And so I have a certain mean pressure here. Okay. If now I imagine, so let's do one at a time. If I now increase G naught, What I'm actually increasing is the heating by photoelectric effect, right? And this will end up, I can change colors and do that, ends up in having, in displacing the curve, well, if I don't do it properly. So if before the mean density of CNM was this one, now that my mean pressure is this one, the mean density of the CNM is this one here. But in this case, what I fixed at the beginning is the total mean density. So here it needs to be fixed too. So when I displace it like here, if this one was something like this and this, I'm already growing. Here, I would need to change the proportion to still have that one. And so basically what I'm doing is I'm decreasing the mass of the CNM. Does that make sense? If then on the other side, I play on this parameter here, then it's going to be the same, right? Because when I go in this sense, I'm going to decrease this point. It's going to stay the same, so I need to decrease its fraction.
Yeah, well, I'm still a bit puzzled about the G0 effect. It's really me who doesn't understand. I mean, in the first case, when you keep the average density constant, well, if you increase G0, I understand that you increase the average pressure. And then you increase the density of the stable CNM. Right?
Yes.
But I don't understand why increasing the average density of the CNM decreases its mass fraction.
Because the mass is fixed. The mass is fixed. And WNM is kind of, how do you say, constant density, a constant volume, the volume that it occupies. So it affects the CNM. It's where you see the decrease in mass. And now to
okay, well, I think maybe I start to understand. I start to get it. Okay, and in fact, I was curious to understand. I think it is in your manuscript. Sorry. I noted the page number, but yes, page 51 in your manuscript. Could you explain me why it seems to me that the cosmic ray heating
yes,
has an influence which is just the opposite as the photoelectric heating? And I was wondering why.
No. That was a good point. I'm like, what does it mean? And then I look and I just inverted the label. So no, clearly. Okay, it doesn't have the opposite effect. What it does, I'm going to show you the right picture. Manuscript, no, it's not this one. It's this one, page.
Sorry?
Thermodynamics. So the right graph is this one, right? So when I increase the cosmic rays, I increase the heating by cosmic rays. So
okay.
And the fact that is not exactly the same effect, like, you know, they are not affecting the curve the same amount and the same way, is because of the dependence of the
that I can imagine that there are a lot of details coming into that. I can imagine that, but I was quite puzzled. Okay, so it seems that the reconstruction of the lines of sight is critical.
Yes.
Because, and in fact, well, okay, so because in Valdivia, I think there was already the self-shielding of H2.
Yes.
Yes, because on your slide, page 18, I was not well, not entirely clear, entirely sure that it was the case, because you were saying shielding of UV photons by dust grains, but so I was a little bit puzzled.
No, and also self-shielding. Yeah.
So I would say, am I correct if I say that, I mean, the engine that you're using, I mean, the code and the basic physics, heating, cooling, self-shielding, I mean, all the was already in Valdivia.
Yeah, mainly yes. The difference is actually so we spent, that's why I talk about it in the manuscript. We spend a lot of time on this curve because the equation.
On which one? Sorry.
I'm sorry.
Which page? Sorry.
Which no,
you were showing something. You spent a lot of time on what? Sorry, I
on the
didn't.
microphysical processes of heating and cooling. So we're taking all the analytical work of Wildfire 95 and 203 to compute to be sure that we have is heating and cooling. So that's the only part that I put my hands on.
Yeah, no, I didn't mean that you didn't change anything. But it seems to me that the critical thing is the reconstruction of the line of sight. And I wanted to be sure that this is the main change which makes the H1, H2 transition from your simulations to look like so much to the observed one.
Well, there's one thing about these microphysical processes that also affects a lot, is that, as I said before, there's now the radiative transfer is taken into account also in the heating processes, and that was not the case before.
Yeah, but are you referring to the shielding by dust?
Yes.
Okay, well, but well, in any case, the reconstruction of the line of sight is very important, it seems. And so I have. Well, I have a very minor question, which must be a detail. You call phi the volume filling fraction.
Yes.
But in your, I'm wondering whether it is the 1D filling fraction, because you compute, I mean, in your manuscript, for instance, page 97, what you say is that you're cutting the line of sight into pieces which are 1 minus phi times some length for the CNM, well, for the neutral medium. But so this is a 1D fraction, right?
Yes, this is. Yeah.
But so the 3D is Q. But so the 3D, I mean, when you quote some values which are half, for instance, I mean, in any case, it may be a detail because it does not impact so much your results. But you say that you take phi equals to half from Hill 2018. But is it phi to the 1/3, which is equal to half, or is it phi, which is equal to half?
No, I think it's phi. It's phi, and then they look. Like usually in these studies, when they do simulation, like Hill and the other ones, when they do supernova simulation, what they show is actually the fraction along different lines of sight. And they give the fraction along the lines of sight.
Okay, so the phi you should take is half to the 1/3, which is 0.8. I mean, that's not a big deal because in any case well, it seems to me, maybe I'm wrong, but from what I understand, you're putting a 3D volume factor onto a 1D. Maybe I'm wrong, yeah?
Yeah, I'm sorry, I'm gonna think about it, but like.
So in any case, I don't think it is critical, but.
In any case, yeah, you remember like how it goes if I change where is it? If I change phi, right?
Yes, yes. But I mean.
Yeah, I'm gonna.
Maybe it's to be clarified later on. I mean, no. So the point, my question is to try to understand. So you have a box which is 200 parsec. That's correct.
Yes.
And then you have lines of sight which are up to 3 kiloparsec. And so, and this makes an echo to a comment from Cécile before regarding the Jenkins C1 observations in extragalactic. So you have 3 kiloparsecs which are the same turbulence, because you take a box of 200 parsec and you stack some pieces of CNM and pieces of ionized medium, right? And so it is not clear to me whether this is local or whether this is some average average property of the turbulence within a few kiloparsecs that you are modeling.
Yeah, that is a very interesting question. So what we're expecting, or what one can expect, is that in the end, since we are looking 3 kiloparsec around, we can expect that, you know, locally the conditions are different, and so that this variability cannot be reproduced in one set of parameters. But in the end, we can reproduce it, and that's probably because it is kind of an average. Like if we are looking at in a certain, we have always an observation integrated values. It's very pathetic, I can see myself. We have always integrated values, right? And so from the observational point of view, it can be an average. Now, what the turbulence does, it's giving us very different conditions that allows to reproduce the dispersion, but are we sure that we are not, that doesn't reproduce it because it's a and it's because it's always the same turbulence? No, not at all. There's
yeah, but I mean, 3 kiloparsecs, it's quite big. I mean, you could cross quite a variety of conditions across 3 kiloparsecs. I mean, you could cross. So it seems that what really matters, it's not the property. Well, I mean, what it looks like is that what matters is the length, okay, and average turbulent properties are okay, and this allows you to reproduce the H1 to H2 transition. And well, this was. I wanted to be sure that I understood well, and then maybe if you talk with Jenkins, you have to keep that in mind, that you have 3 kiloparsecs of average turbulence. And I have another question about the forcing. So you said that the forcing is, well, you didn't say that, but I understood from what you say that you mean that the forcing is independent of the magnetic field. Ah, yes, because there was a slide where you said weak dependence and strong dependence, and B was on the weak dependence side. And so I was wondering whether the forcing is really independent of B.
No,
because the forcing is on the other side.
Yes, so I didn't say, I didn't mean to say at least that the forcing is independent of the magnetic fields. What I mean is like the forcing, what technically is, it's like an acceleration term divided in the rotational solenoidal modes, as I want, but it's an acceleration term in the momentum conservation. Then what happens to the fluid, it's magnetohydrodynamics. So one can affect the other, and I think they clearly do, right? Because they are coupled. What I mean here, weakly dependent is the transition. So the transition of Eva H2, it's strongly dependent on these parameters and weakly dependent on this. And this was coming from here, where so I skipped it, probably since I had 1 more minute, I should have done it. But in which I show that, for instance, the simulation and the observations give approximately the same, the Kingerfish diagram simulate very well the observation when the magnetic pressure is lower than equipartition, and then it doesn't work. So that's what I meant, that it's weakly dependent, because in a certain range, we can't constrain the magnetic field with H and H2. So we need other observable. That's what I meant with weakly dependent. And same thing here, right? So I remind you that big KS means that simulation and observation are very different. And in case in which we are more compressive than solenoidal, for instance, we can see that turbulence doesn't affect much this transition.
Yeah, but I mean, so maybe just to reformulate, maybe I'm completely wrong, but I mean, the fact that you have compressive or solenoidal, is it completely independent of the B-fin? Physically?
How I put them in at large scale is. Then how they evolve, it's MHD, so they are not, right? They're coupled.
Yeah, okay.
So it's like how I introduce them. And it doesn't mean that it's the same in all the, that's what I put at large scale. So it's an acceleration, random, etc. And it's what I insert at large scale. Then the evolution, it's MHD. We don't touch it, it's physics.
Yeah, well, large scale is 200 parsec, so it is.
Yeah, 100 parsec more.
Yeah. So I have one very last question. It's about the ortho to power ratio of H2.
Yes. Okay.
In the observations, do you observe, well, do they, the Gunedanavar, or Gunedanavar, yes, do they observe only one symmetry or do they observe the two? And if they observe only one, did you have to assume an ortho to power ratio?
Okay, so Gunedanavar is a compilation, so I didn't do any observation. So it's an ensemble of different observation, Copernicus views like Gilman, etc.
Sorry, I didn't understand. Sorry. I didn't understand.
Sorry, Gunedanavar, it's a paper, it's a compilation of different observations.
Different
observers. In which, for instance, for H2, it's Gilman, Savage, etc. I'm not sure now that you ask it, that is for everyone, but usually what they observe is it's both. It's different. It's in the UV, so it's different lines. I don't think we need to assume anything on the ultra and power ratio.
Okay, so what you say is that they observe both, and so you really have access to the total H2 with no assumption.
Yes, because they observe a lot of lines. Yeah.
And so in the future, do you think you would be able to put ortho para conversion reactions of H2 and of H3 plus? I mean, H3 plus, the ortho to power ratio of H3 plus in the diffuse ISM is a puzzle. And I mean, it would be interesting to check whether you would be able to reproduce the ortho to power ratio of H3 plus. So this is one thing. And the other thing, and still related to chemistry, is whether you would have some tracers to propose for this CH plus at a low column density. I mean, CH plus is probably not the right tracer because it is not abundant enough. But do you think you could have some tracer of this gas? And is this gas the stable CNM, which you showed in your pressure density diagram?
Interesting.
Yeah,
so, okay,
the second three questions in one.
Remind me. But also the first one. Yeah. So for H2. So I think. So I don't know for. Even for H5. So in the end, like now, as you see, the excitation code of H2 exists, and the missing part is computing it. Is to compute it compute the chemistry in which H2 is included. But so at least as post-process, computing the ortho-para ratio of H2 as the code is done, it's something that it can soon be done.
Yeah, but it is computing the ortho-para ratio due to the excitation, if I'm right. Well, the excitation is not going to change the ortho-to-power ratio. Well, it's only reactive collisions which change it. But maybe it is too much of...
No, what I mean is the orthopower ratio is given by collision or all the other processes, right, that are responsible for the excitation. So by computing the excitation of H2, taking into account all of these different reactions, you can compute the orthopower ratio as post-process.
Yeah, well, I mean, it is trickier. I mean, but we should talk about that. But so on CH plus, so it is on page 47 on your slides. There is this low column density CH plus, and there is this, and I wanted to know whether this corresponds to the CH plus, which is in the CNM branch.
I'm thinking about it. No, I really don't think so. I think it's still linked to the diffuse part, because in the end, having such a peak, we wouldn't create such a peak with CNM. We wouldn't create such a peak in CH plus and not in the column density. So we would obtain higher column density.
Okay, so but it is.
So I think more. Yeah. Okay. Sorry. Yeah.
No, but okay, I understand your answer. But so it is still tempting to understand what is this red clump in the bottom left corner.
Yeah, so it's, as we can see, it's bimodal, and I think this bimodality comes from H2. So I think it corresponds to the zone where we also have the low bump in H2, and actually many chemical species, not all of them, but many chemical species in our nectar, when we compute the column density, show this bimodality. And so if we go, I'm thinking out loud here, right? So if we look at this low density one, it's the zone. Well, here it's just one cut, but I think it's the part of the graph that is diffuse enough so that the column density, the total column density, is still low, but is diffuse. And since we have seen that this, I'm moving too much, I can't follow my line now. 38. I think that bank would be linked also to part of what is happening here. You know, so that it's warm is intercepting a lot of warm and diffuse gas, so that you still have low and diffuse column density, so low column density, but it's still intercepting a gas with enough CH plus in the mean. It doesn't mean that the fraction needs to be because the fraction is very low.
Okay. So I'm done. Thank you.
Okay, thank you, Pierre. Okay, now maybe a woman. No, Sarah, are you ready? Can we hear you?
Yes, yes, I am. So first of all, I would like to congratulate Elena. I am, of course, in the jury, the person that is less expert of the field. And I found your presentation extremely clear. I have to say that it helped me to clarify points that were not completely clear by reading the thesis. That also shows that you have capacities in explaining things. And so congratulations for this effort. And I have a few very general questions concerning in particular the perspectives. So as a non-expert, I was wondering, in this kind of studies, from the observational point of view, what would you see as the most promising kind of observations that could give important feedback to this kind of studies that you have been conducting?
Thank you. And so we have there like a lot of observations, right? Like many wavelengths, like especially like atomic and molecular tracer. I think that Some of them can already be used to conduct this study. And but since it's a statistical study, it would be like very interesting to extend this observation, right? I have the impression that I'm really not an observer, so I hope not saying something very stupid, but before it was like usually there is like one observation and then one chemical model, etc. So there was less the needs of not repeating observation, but observing the same thing in very different parts. So I think it would be interesting to extend the study in general for the molecules and atoms that are in the diffuse part, but extend in general all kind of observation, also because it's so rich that in the end, kind of in whatever wavelengths we are watching, there's probably some signature of some species. And I don't know, yeah, so I think that's...
And so I don't know if it's something that you have been studying during your thesis, but for instance, the CH plus upper limits, do you see any observational perspective to significantly improve over the next years the capacity to lower the threshold of detection of CH plus, or there is nothing significantly new in the observational panorama to improve that kind of detections?
Okay, so these observational CH plus have been done in absorption in the UV, and clearly these upper limits are linked to the telescopes that I know of in so that kind of study, so it's absorption of UV light. I don't know of any telescope that's gonna give us soon data like LUVOIR, but it's gonna be in 2035. And so then I'm not an expert. For CH plus, it would be interesting to look at the first transition in emission, because that's probably the only thing that we can do, hoping that the fact that is not that is in the outer shell of the CNM, because it's where it's already transitioning to the out equilibrium gas, would actually make it like feasible. But then I don't have like any technical. I think the transition in I knew it at some point. Where was the transition? But I think can provide.
Okay, thanks. I know that this kind of non-expert questions sometimes are more tricky because they are less focused on exactly what you did. But it was a curiosity for me because indeed I was wondering how these kind of studies can be improved in the future. And probably just another point on the methodology from the numerical point of view. So I understand that you have pointed out, as it's written here, that you would like to extend, or in any case, it would be nice to extend to other atomic or molecular tracers. And in terms of capacity of performing the numerical simulations, are there any limits in computational limits for which, for instance, more powerful machines could help in improving the simulations, or at the moment there is not the significant limitations in terms of technical limitations for the simulations that need to perform? It's just a matter of time to introduce more ingredients.
So for this particular work, like even to touch this point can be done at least in first approximation, like at the beginning, with the parametric study that we have done, because the simulation are already there and the column density of all these pieces are already there. The main point is to have the observation and to compute, which is not really that super tiny work, because it's basically we don't do our own observation, right? We are taking other observations, so it's just like computing, so the having the information of the distances, etc. and numerically build these lines of sight and doing the case test is nothing. So it's really like
Okay. Yeah.
the simulation. Then there is one point is that all these simulations are done at moderate resolution, and at one point we will encounter, but also as we did with the population of C1, that we have hit the lower limits of the resolution and we need to increase it. But for now, for this kind of study, I think for now, for literally to do this and to continue this, I think we have the numerical power. We have also the numerical power to go at higher resolution. Then if we think, for instance, of the problem of C1, if it's something that missing in the simulation, like for instance, I don't know, shocks, J shocks, or things like that, like this, we would need for that higher resolution, but such a higher resolution that I think we can't reach right now. But again, there's like some way of avoiding and treating it as post-processing. So in the continuation of this, I know that there are lots of limitations due to numerical simulation that we can reach, but I think that in this work, staying coherent with that, with all the approximation that I explained before, it's doable.
Okay, so probably a very, very last question on my side that is again on the methods. From the statistical point of view, I found very interesting what you have developed in terms of KS test. And is there anything in the literature about any kind of other statistical tests that could be used to compare what you have got? Or is anything planned about applying other methods, or do you think that this could not bring to something significantly different?
I think so. I actually don't know for other methods, and when I did come up with this, was really like the only thing. Like I remember when I discovered KS, I'm like, oh, I could maybe use this because I don't really see in 2D what we can do, but I didn't dig that much into it apart from the beginning. And then apart from comparing to other methods, I think there's a lot of improvement that we can do on these KS tests, on stability, etc. Also to try to include the error bars, for instance, of the observation, because the observations sometimes like have very big error bars.
Yeah.
And then I didn't show it here, but for instance, since for CH+, since there are only upper limits at a certain column density, I already modified the KS test, because that was a first essay, to take into account these upper limits, but then again you do other assumptions, etc. So I think like most of the work now should be like from that point of view, improving this one, this test the stability and the error bars, because I think it's very important. So
yeah, no, I agree. I fully agree. Yeah. Okay. Thank you. It's all on my side. Thanks again.
Oui, bonjour, vous m'entendez? Alors, Elena, félicitations, bravo. J'ai bien aimé la présentation aujourd'hui et puis encore plus le manuscrit, je dirais. Hier, j'ai pas vu le temps passer. J'ai passé ma journée à lire ta thèse et c'était vraiment un plaisir. J'ai appris plein de choses et j'ai vraiment apprécié cette lecture. L'ampleur du travail est vraiment, c'est très impressionnant ce que tu as fait. Le papier le papier principal qui est publié, c'est un papier très important pour le domaine, et ça, j'en suis persuadé. Je voudrais te poser quelques questions, d'abord sur le chauffage et le refroidissement, un peu pour poursuivre un peu sur ce que Pierre t'a demandé. dans la description des processus de chauffage et de refroidissement que tu fais dans ta thèse, tu parles de la dissipation d'énergie turbulente, qui est mal connue et qui est intermittente, on le sait. Mais néanmoins, on n'en tient en général pas compte dans l'évaluation du chauffage et de refroidissement. Ça ne fait pas partie. Ça fait pas partie c'est pas dans les termes de Woolfire, il me semble en tout cas. Mais quand on regarde la quantité d'énergie qui peut être impliquée dans le chauffage de la dissipation de la turbulence, c'est une quantité qui est importante. Alors, je voudrais savoir si tu avais quelque chose à dire là-dessus. Et puis avant que tu répondes, aussi sur le chauffage et le refroidissement, un peu plus tard dans ton manuscrit, je crois que c'est à la page 50, vous faites une étude des différents processus sur la courbe. C'est d'ailleurs très, très intéressant cette section. Il y a une phrase qui m'a un peu surprise où c'est écrit que tu as écrit que c'est vraiment l'effet de l'effet photoélectrique sur les grains qui conduit à la bistabilité du milieu et que sans cet effet, il n'y aurait pas de phase. Et moi, je me souviens des papiers de Field, il n'y avait pas l'effet photoélectrique sur les grains. Et il y avait 2 phases, alors il y a quelque chose que j'ai loupé là. Et j'aimerais que tu m'expliques.
Alors, du coup, alors, je peux passer en anglais ou pas?
Oh, sorry, I should have talked in English, yeah. Well, I'm really sorry about that.
No problem. So, for what concerns the turbulent heating is not included, right, in this simulation.
Yeah, that's what I thought.
It's not a term in the heating. It is one of the heating that I presented. I don't know if you've noticed. It was like a blank triangle, which means that it's not included. And yeah, so the problem of including it is we need to do some kind of assumption, right? Like on the scale, on how much, especially now that there are like this many observations on intermittency, etc. So I think that in the end, it's a good thing that it's not included. But on the other side, the simulations are distributive, right? So there are still some kind of heating then from the simulation due to turbulence in a sense.
So you're talking about the numerical dissipation. So that yeah.
And for the I wonder that's too how, because it's in the 1969 paper of they're looking at the heating of cosmic rays, because at the beginning that's what they thought that it was heating. But I admit that I didn't look at their equation in detail to see. But so my point on without the photoelectric effect, we don't have the stability, is because in the set of equations that I'm using, if I put out that term, I end up. So I didn't look at the other condition, like outside of this graph. But if I take out the photoelectric effect, I end up on this curve, which clearly it's monotonic. It's true that I didn't look at, if there's some stable one outside, but that's what I meant. Should probably rephrase the sentence.
Yeah, this is puzzling, yeah. If I remember correctly, and Patrick and Benjamin know that probably, the cosmic ray rate was much higher in the Field paper compared to what we use now. But the cosmic ray heating is independent of density, which is not the case of photoelectric effects. So the curve is different. Well, I don't know. I don't know why it's okay. So that's a puzzle. Okay. I would like to ask you about the CNM to WNM fraction, and this is something I could not really grasp from your figures, or I mean, you talk a lot about the H2 fraction, which is really the observable you're trying to reproduce. And I would like to have a feeling for your fiducial simulation, what kind of mass is in the WNM? What's the fraction of the mass in the WNM?
So I don't have the fiducial simulation here, but so this is in mean in the simulation how the fraction in the different mass goes.
Oh,
And usually I would say that we have kind of a high fraction of CNM. So right now I don't have in mind our, I'm gonna put
yeah, it's like 80%, you'd say.
Wait, I'm gonna put you there. Why am I keep closing the phone again and again? Okay, so steady states. So these are CNM is down and WNM is up. So our fiducial simulation is this one here. So around a little bit less than, sorry, yeah, a little bit less than 17% in mass. But then again, it depends on the simulation, what we define CNM and WNM, right? So because they do a cutting temperature
at 300 Kelvin. So I think that's fair. It's okay. So that brings me to the question about the observations. I know this is not your area of expertise, and you did the thesis that is mostly based on numerical simulation, but the originality of your work is the comparison to observation, and I think this is very important. So you're using a data set which I looked at the paper. There's 3,000 stars in this data set, and you have selected 360.
Yeah.
Based on some criteria that I could not really understand. So I would like you to comment on the criteria for the selection, and also on the representativity of those lines of sight with respect to the diffuse ISM, because this is a really important point, because the volume you're simulating is a big volume, so it should be representative of really a big cut of the Milky Way around the sun. So it has to be representative of that type of volume, what you're simulating. So do you have the feeling that the data set you are selecting is representative of the full physical condition we see in a volume of 200 parsecs around the sun?
Okay, so I didn't select the data, meaning that between these 3,008 stars, so it's a catalog of many observables, so not all of them at H2. And some of them, I don't know if those 3,000 were like double, because it's a compilation of different measures. So if they have measure of different people, you know, it was like the same source, different times. And then the only real criteria was to exclude the sources in the gas, the one intercepting the gas associated to Magellanic Clouds, and all the high redshift galaxy and extragalactic contents. So I would have preferred to have, apart from the example, looking at all the papers, but I would have preferred to have like 8,000 or 1,000 or 800 sources. The more the merrier, right? So it was not a selection. Like the selection was only to have like a local ISM to be sure that we are not testing another galaxy with a gas that's probably in very different conditions. And but otherwise there was no other selection. I didn't exclude any sources that they were there.
Okay, well it's kind of surprising that you go from 3,000 to 360 just by excluding the Magellanic area, high redshift galaxies. And you say there are some doubles. I can believe there are some doubles, but I mean, they say it's 3,000 stars, so they're not saying it's 3,000 observations. So yeah, well, there's something I don't get here, but okay. And about the representativity of this data set, can you comment on this?
Yeah, so all this study is done effectively imaging that it's like random and that they are representative of the sky, right? And we are so we have looked and where they are positioned in the sky. We can see that it's all over the sky, all different latitudes and the different quadrants. But then, is there a bias? Probably. For instance, we have no lines of sight. Sorry, I was looking for the thing. And we have no lines of sight at density column density higher than 10 to the 22, and that is due to how it's chosen because it's because of the observation of H2, the limited that they have with Fuse and Copernicus. So probably like that's something that we were like really, I don't know, to struggling on spinning like that. It's like, how do we, is it like in this zone, if my simulation are putting a lot of breadcrumbs in that zone, is it bad because, you know, we don't have any observation and so that's completely wrong and we are simulating something that is not realistic? Or is it just the lack of observations? And that what pushed us and doing this KS test, not looking at all the points, but imposing that in each quadrant there are at least 10 observations to try to limit this border effect.
I'm not too worried about the high column density cutoff. When I look at this, if I collapse this 2D PDF on the NH axis, I see that it's going to peak at a few times 10 to the 21.
Mm-hmm.
My knowledge of the high galactic latitude sky is tell me that this is high and that the column density would be peaking below 10 to the 21 in the solar neighborhood. But so that's, and there's much more space, much more lines of sight with low column density than lines of sight with high column density.
Yeah,
so that's it. So that's why I was asking the question of the low number of stars in the sample, because I was worried that you had made a selection based on the detection of H2 or the observation of in UV. And if it's based on the selection in the for stars for which there were observation in the UV, that's a bias towards the lines of sight where, well, no, it's not a bias, no. But,
yeah, but that's what is done here, right? It's all observation in absorption in UV.
That's the selection, yeah, okay, yeah, the selection. But yeah, if I look at this PDF, it gives the impression that there's more lines of sight where H2 is detected than lines of sight where there's no detection of H2. Would you agree with this?
Yes, yeah. It's like more than 300 on one side and less than 50 on the other. But then it depends, like this column density, it still makes sense to me because if you look at the latitudes, those high is actually gas close to the midplane, right?
Yeah.
So those are not high galactic.
Okay. I'd like to ask you a question just before going to a numerical simulation. I'd like to ask you a question about the pressure, not the C+ pressure, but there's a figure in your thesis where you show the pressure that is dropping rapidly when you start a simulation. I've seen that also when I did the same kind of simulation. When you start to form CNM, the global pressure is decreasing. You know what figure I'm talking about, or no, you don't?
No, I don't.
It's let me see. I tell you, it's figure 5.6.
In the manuscript.
Yes.
Mm. Yes.
So yeah, you see the pressure goes down and then it stabilizes as CNM starts to form. Many studies have seen this effect in studying the multiphase. And I'd like to, well, I don't know if you've noticed this and if you were puzzled by the fact that the pressure is decreasing. And my question is also, do you need to start with an overpressured medium to produce CNM and H2?
Okay. So when we start our simulation in a completely diffuse WNM environment, right?
Yeah.
And so that's why the pressure is so high, because it's very hot. Okay, so we start basically on this graph. We always start in condition up here. And before doing all this study, what we looked, for instance, is like what's happening if there is no turbulence. So how does it go down and how it's divided into phases when I'm not perturbing it? And what it does, so it goes down. I'm sorry, I'm going to do another one here.
Yeah.
So in that case, so if I start from here, somewhere like it goes unstable. What he did in the simulation was like going here and then divide in two. And when it divides in two and it goes here and here, it's something that depends on you. It's something that maybe could explain this lowering the pressure is that while this one just goes directly here, this one goes like this. And then it restabilizes again and it goes higher. I'm talking about the simulation without any pressure. And this thing here, I think it's because this medium, so here we are in the cooling, right? The cooling zone of the graph. And the isotherms are like this. And what I think is that the cooling is this part, since the gas is denser, is actually pretty fast. And so it's kind of the tendency to go to the gradient of the temperature. And that's why we have that. And once we are here, since it hits here, it clearly puts down the pressure. And then it gets like a little bit more. And I think it's that, but then it's just my, interpretation. So I don't know.
That is making sense. And but it opens, it goes into the question of the dynamical conditions that is creating the condensation of the gas. And so it seems that you really have to have overpressured WNM at some point to create CNM. Would you agree with this? And I'm still puzzled. I don't know how you can have such high pressure in such a big volume, or I mean, I don't know if you thought about this, about the origin of the condensation. And what is really
what we started is like, so we impose the mass in the simulation, right? So once we impose the mass, this one is fixed, and since we want WNM, we just put it back there. So we've never started in condition like, you have something down there. So I have no idea. But like this, I would say like, yeah, it's gonna heat up because it's in the heating zone, and then it's gonna do kind of the same. But yeah, I have no idea. We don't look at it.
So just to continue on this, there's this wiring paper, WARENG. There's this guy who's also making simulation of thermally unstable H1. He published a paper last year, and he also noticed this decrease of pressure, and even used that to say that this is enhancing the formation of CNM, because if you have low pressured CNM cloud immersed in a higher pressure WNM, the gas will flow to the colder regions, and that would even increase more the density fluctuations and enhance the CNM formation. So I thought that was an interesting idea. I don't know if this is making any sense, or if it's an important.
It's difficult to see what's the cause of what's the effect, right?
Yeah, exactly. I agree.
That it would be like more the opposite, since it's like cooling faster. It decreases the pressure.
And my last question is about the numerical resolution of your simulation. So I see that you've conducted a lot of 256 cube simulation, and that's basically the fiducial simulation you're using is at that resolution. So for 200 parsec, that's a cell size. Yeah, it's not super big. In observations, we see a lot of features and CNM structures that are smaller than a parsec, and there's quite a lot of that. In fact, it's very much structured at that scale, at the scale of a parsec or below, in the local ISM, and also higher contrast and density are expected at small scales in this type of physics. So, have you made any numerical experiment at higher resolution to try to convince yourself that the setup you're using is the right one?
Yeah, so for what we're doing, it seems to be the right one, meaning that even with C1, we know that we should increase the simulation. So what we started with was IMR. We did some simulation. We've never been higher than 10. So 1024 cube. So I am convinced this is the right setup for what we are doing right now. It doesn't mean that, so we were focusing on H and H2, right? That was our starting point. So when we did our parametric study, because we were convinced that it didn't affect H and H2, also because we also had like simulation at higher resolution, then this doesn't mean that it's not gonna affect other observables, like when you're gonna do the column density of something else, like even the population of C1, we would probably need to run higher resolution. And technically, like actually, the most of our simulation are done in both 127 and 256. Then we use as fiducial simulation the higher one since we had it, but we also convinced ourselves there.
So you saw no impact on the fraction of H2 by increasing the resolution.
But it affects the fraction of H. So not the column, it's different because it doesn't affect the column density of H2. So the integrated kind of fraction, but it affects the quantity of warm H2, for instance. At least, not on 264 parsec, but since we also went lower, if we go too low, we can see that, you know, CH plus is not good at all because we have this lukewarm medium that is artificially increased.
Okay, thank you. I will stop here. Thank you. Thank you.
Thank you for the answer. If you permit, I will, because I am the last one, I did not work closely with Elena, so I have also a few small questions. But before, I want to join the congratulations. I am particularly pleased by this connection between this state-of-the-art simulation and the data. And I think it is paving the way for further studies, especially now because of the improvements in the distribution of in the Milky Way. So it's really pioneering work. So congratulations. Well, my questions. Well, this is curiosity. Well, and this is an answer also to Marc-Antoine. Marc-Antoine, I think the big number of line of sight, but it is for all species together. So there is a limited number of measurements of H2 and I think Elena took all of them. You are not convinced?
Have you heard?
Did you hear? No,
I did not hear you. Sorry. So yeah, please repeat. I understand you're talking about the sample. Yeah.
This compilation is assembling a large number of things, and even in the optical, in the UV, etc. So this is why the number of line of sight is big, but the number of line of sight for H2 and H1 is limited, and I think very limited. It's about a tenth or something like that. Unfortunately.
Okay, but for many lines of sight, there was EB minus V that could be used to estimate the total column density, and that's over the sky. You have all the sky in EB minus V using the dust. So yeah. Well, okay. That's I should not talk. It's not my turn.
Of course, no, you can, of course.
Yeah, no, for the total column density, it comes from EV, it comes from measurement of H1, that can be the sodium, etc. But what was more, were missing the most was like H2 in the end. I took like all the possible that I could take. If I had more, I would have used more.
Okay, so about this data, did you have the time to look at the location and the specificity of the outlier? I mean, you mentioned in the document that there are a number of points that do not fit. Did you look at so maybe it would be interesting. I have to say that for knowing this compilation, there are a number of typos and small errors. Yes,
I know. I spent 60 minutes.
So I would not be surprised if some of your outliers were simply bad numbers. Okay.
No, but technically what I know is like...
Okay, unfortunately, it does not affect your study, but this is it has to be read carefully. Still about the data, the Magellanic clouds, you remove them? I don't know, it's curious. Do you remember if they are NH2 measurements for the Magellanic cloud mentioned in this compilation? Okay, because when this is from the point of view of the perspective, because the Magellanic clouds are a very different medium, not the same metallicity, same total pressure, same ionization, etc. And conducting a simulation, if there are enough data, would be interesting because it's quite a different. About well, still about the possible outlier, they are this YSO, young scalar objects, like that, RB objects, because they may have H2 associated to the circumstellar. Now I have a small question about the cosmic ray ionization. Did I understand well that it did not vary the big set of simulation? It is unique value.
Yeah, it's a unique value.
And classical value.
A classical value, like the most recent parameters, they are. Okay.
But the most recent values from H3 plus.
Yes, exactly. Yes.
Because there is a small indication that there is big variability because Voyager is measuring now really well the spectrum, going down to 1 MeV. So, and there were studies from people in the APC, and they tried to understand if, for example, there could be a bunch of cosmic rays between 100 keV and 1 MeV to understand to explain the big ionization rate, because the conclusion is no. So that means that locally, the cosmic ray ionization rate is between 1 and 2 orders of magnitude smaller. What we did, okay, assume that you would have used 10 times smaller ionization rate. Would it change a lot, or is, as you were answering to Marc-Antoine, is heating by dust rain the most important, or would it change something?
Yeah, it would still change. It would change because it would change. So all these thing that I explained,
yeah,
it was like changing this curve, right? And this curve would also be affected by cosmic rays because it would increase or decrease the heating, right? But mainly in this part of the curve. So like the main assumption on the fraction of CNM could be similar, but there is another important, because cosmic ray not only fits our medium, right? They are in many chemical reactions.
Yes.
So it would also, I think, affect the chemistry. So that's one of the other parameters that we should look into.
So maybe one day, or I know that simulation require a lot of time, but it would be interesting to see what happens if there is that is a surprise, because the local environment is not well, we do not expect, because they were supernovae, not far away, it's a bubble. So we do not expect to have a low quantity, or a small quantity of low energy. Mystery. One more. I have a small question about, well, as Cecile, I am interested in C1 and in the, because it's such an old-standing problem. It is surprising. Well, it is, well, there was some hope that this type of simulation would explain, but no. So I think it's a very important problem. It is a very important problem, because that means that the solution is to be found somewhere else.
Excuse-moi, Rosine, on t'entend très difficilement. Est-ce que tu peux te rapprocher du micro ou moins bouger?
Ah, Cécile.
Chaque fois que tu bouges un petit peu, on te perd. Je ne sais pas ce qu'il faut faire, mais...
On t'entend, Cécile.
Répétez, on n'a pas entendu.
Moi, vous ne m'avez pas entendu?
Non, pas maintenant, là. Tu peux répéter?
Non, ce que je disais juste que Rosine, on ne t'entend pas. On ne t'entend pas.
Ah.
On ne te comprend pas. Enfin, moi, je ne te comprends pas. Je te perds beaucoup chaque fois que tu tournes un peu la tête.
Ah, c'est parce que je bouge trop la tête, ça c'est mon défaut. Et là, ça va?
Ouais, là c'est mieux, merci.
Bon. Oui, non, je disais où j'en étais sur le. Je disais aussi que j'étais très intéressée par le problème du C1, excité, et que en lisant la thèse, m'était venue une réminiscence. Donc, je ne sais pas si c'est une piste à explorer, mais puisque c'est l'occasion, je vous pose la question. Il y a des réactions d'échange de charge C+, H, et puis dans l'autre sens aussi, C, H+. Bon, peut-être, il n'y en a pas énormément, mais une des caractéristiques des réactions d'échange de charge, c'est-à-dire quand un ion pique un électron, non pas libre, mais il le pique à un autre atome, l'état post-échange de charge, de celui qui vient d'être neutralisé un peu plus, par exemple, en l'occurrence C+, qui devient C, cet état est excité. Et bien plus que c'est montré dans les études de cascade périodique, d'échange de charge. Et ça a été assez bien étudié. Et la caractéristique, c'est vraiment que ça tombe sur un état, que l'atome formé, neutralisé, est dans un état excité. Alors, est-ce que c'est le nombre la quantité de réactions d'échange de charge est suffisante pour changer peut-être ces rapports, ces quantités d'état? Si j'ai bien compris, il n'en faut pas tant que ça quand même.
Genre, ça dépend qu'est-ce qu'on veut. Si on veut déplacer toute cette partie-là au-dessus, ça veut dire que par chacun de ces lignes, on doit avoir des points super hauts.
Ouais.
Mais par exemple,
parce que la réaction d'échange de charge, là, c'est pas encore dans le suivi. Celle-là.
Non, et celle parce que je fais quand même pour les Italiens.
Sorry, I switched to French. Oui, okay. On continue. Non, continue. En anglais, peut-être.
The chemical, there is a chemical pumping, but it's something that they do based on this structure. So it's something that they do, it's at equilibrium, so there's no that's implemented. But there's kind of reaction included in the chemical. But there's no excitation associated to it.
Okay. Okay, so maybe because it's such a embarrassing, well, it's a problem that is such long-standing. And my last small remark is about the local structure. There are many surprises about the local structure, and there are also recent results from Gaia showing that the Milky Way is absolutely far away from calm, from being calm. There are plenty of effects, ripples, and many are due to mergers with small galaxies or dwarf galaxies, mergers with globular clusters, even globular clusters. And so if locally, it is now known that the structure is very complex, and they are big vacuum regions, and it does not look at all like spiral arm, classical spiral arms. So my question is, again in this simulation, is it possible to introduce force turbulence? Can you, for example, simulate, like for example, the crossing of a big object by a massive object, because you have gravity, so crossing of a massive object of the simulation, and see what if it could explain, because you will have a lot of perturbation, and this is you may have very strong velocity of the impact. I mean, if it is a crossing by a globular cluster, there are hundreds of kilometers per second. So you may have introduced very unstable. So I will stop here. Congratulations again.
Can I add just one thing for the Gutenberg catalog?
Yes?
Yeah, so I know that there are like so many typos, and when I got one, in the end, what I did is like going to look at every page here is citing and correcting all the citation that didn't exist and all.
So you should.
We hope that at least that one shouldn't be a problem because I typed each one.
But so if you did that, you should publish the corrected.
So yeah, we published it's published with the article. It's published.
Oui, but you're for the NH2 object.
Okay. For the NH2 object. Good. This was original.
Okay. So now maybe who is starting? Maybe advisor, you want to?
Okay.
I guess you don't have a lot of.
No, I don't have a lot of questions, but it's almost I won't ask you any questions. We are just here to say some messages. So I guess the first message I want to say is that we asked you, Michel, Patrick, and I, 3 years ago, to do a very complicated thing. In fact, we simply asked you to study the chemistry in the interstellar medium, but as you discovered, to treat the chemistry, you have to treat the dynamic of non-steady state environments. You have to treat, of course, the chemistry at equilibrium, out of equilibrium. You have to treat the excitation of species, atom and molecule. You have to treat the radiative transfer. You have to do all of that in 3D because otherwise it's no fun. And in addition to that, because it was too simple, we also asked you to compare all theoretical results with observation. So different species observed, different wavelengths, different telescopes, different facilities, different technical characteristics. So I guess what I want to say here is that usually it takes years to get the expertise of each of these domains separately. And we basically ask you to be an expert of the entire thing in 3 years. So, keeping in mind also that when you started your PhD thesis, you didn't have any background in astrophysics, and that also you thought you have been teaching for the first years of your PhD. So I guess the take-home message I want to say here is that congratulations for not giving. Really, the learning curve was very steep. And we kept moving forward, and we kept accumulating all the knowledge we needed to solve the problem of this part. And in the end, you provided results, very original results. And most importantly, I think a very unique methodology, which will be very important for further studies in that area. So the second message I think I would like to say is that during your PhD, during these 3 years, you have shown a great skill, in fact, in manipulating and developing numerical code. And so your excitation code, with the tools you developed to study observation, and simulation. And every time you try to minimize the effort, in the sense that to try to build a model as automatized as possible so that you could use it during the entire PhD. And as a matter of fact, this is what happened. All the code that you have done, you are able to use them to use the entire PhD. And I think that this autonomy on the numerical side of the thesis was very useful for the thesis, but would be very useful for you. An important message, another important message, and I think that all the people who are on Zoom right now will not understand if I will not stress this message, is regarding your character. So you know that, but you are a very joyful and resilient person. In fact, you are a little bit like the medium you are trying to model. You are highly dynamical, out of equilibrium, full of energy, and well, yeah, well, you can say it that way, but my way was positive. And so, in fact, it was great to work with you for the past 3 years. And it was great for me. I think it was great for your colleagues because naturally you bring life, you bring motion to your surrounding environment. So I guess, yes, well, I speak for myself, but I think I also speak on the behalf of our small team at TNS. So, yeah, the message here is that your presence at TNS would not have gone unnoticed. And lastly, we finish on that. My last remark will be a statement of personal gain. So I know it's your PhD thesis, but well, I have the floor, so I can say whatever I want. And the fact is that working with you during those past 3 years made me learn a lot of things about the ISP, about its structure, about the chemistry, the importance of governance, thermal instability, you name it, I mean, a lot of things. And to the point that now I have a very different view of the ISM that I had 3 years ago. So I guess that what I want to say is thank you for this work in these past 3 years and for everything we have done. I didn't succeed.
No.
Yes. I kind of agree with what Benjamin has been saying. What I would like to add is I always try to emphasize one aspect that I found particularly remarkable, the strength of you are for 2 minutes, you are still students. I mean, I found your talk was exactly what Benjamin described. It was very lively, very nice to hear, and very accurate. And I think you really have a quality in spreading science. Okay, one can really feel that you are at ease, that you enjoy yourself, and this joy is something that communicates, and that's a very important characteristics, because we all scientists, I don't know what your friends thought during the talk, but this is incredibly boring in itself. You know, it's plenty of numbers and so on. So you are sleeping, but then you see, I mean, having this enthusiasm, showing how that you can be excited about all these numbers because there is a message behind it, story that's important. This is actually extremely important for scientists. We should not stay in our lab. We must spread what we found, and we spread message. It is really, and I think you are you really have a brilliant career there. I think as you see, science spreader or yeah, I think so. This is something you should consider as a very strong aspect for the future.
Okay, so I suggest a few very brief words because actually I've been the administrative advisor mostly, but the advising work has been done, essentially by Benjamin and with very strong help from Patrick. So I was about to introduce their contribution, and finally I'll try to give a few concluding words. So although I have not been very much present and have not participated participated a lot in the study that you have embarked upon. It's something that is very dear to me in the sense that you have addressed problems which are very much at the heart of our understanding of the industrial medium functions. So the results are very disappointing in a sense because we thought that we are missing resolution for some subtleties, and we also, or you also provided a very schematic view of the intercell medium, piling up small, not that small stones of patches of medium. And that's not very realistic, as you know, actually. So, so not only 3 years to learn all of that and the tools, and also we develop the capability to show things and make excellent illustrations and presentations. But also you did the work. You did not only learn, as Benjamin was saying, complicated things, but you also did things within this world. And that I think very important. And although you've opened questions and there is plenty more to do, at that stage I think that you can congratulate me very much. I'm nothing here to say that.
Bon, alors techniquement, là maintenant,
Moi, je reste ici.
Oui.
On sort.
On sort, mais le public va
Non,
devoir
on sort.
partir.
Je peux.
Est-ce que le jury peut faire une pause?
Alors.
Est-ce que le jury peut faire
Et
une pause?
oui, le jury peut faire une petite pause.
Dans tous les cas, toi, tu peux tout fermer, non?
Oui.
Donc, tu fermes toi la public section.
Et ça, on risque de...
Donc, on vous invite, donc, on vous invite à retrouver la session publique si vous voulez avoir une diffusion du jeu. Dans, je ne sais pas, je ne sais pas, une heure, une heure.
Non. Mais dans tous les cas, il reste une heure avec moi, quoi.
Donc, on va laisser la session publique ouverte. Mais on va couper bien sûr les micros, et vous n'entendrez pas ce que vous faisiez pour l'instant. Mais pas, on verra.
Alors,
Tu as la moitié ionisée, la moitié neutre. Après, il faut que tu construises effectivement. Donc, si ton milieu, c'est juste des couches plan parallèles, c'est évident. Si c'est le milieu interstellaire comme il est, c'est plus complexe, bien sûr, mais il n'y a pas ton facteur racine cubique de phi. Tu vois?
Ah ouais.
Enfin, je peux me tromper moi aussi. Hein.
Je suis assez d'accord avec Michel, moi, je pense là-dessus. Là. Il n'y a pas de cube là.
Moi aussi.
Je ne me trompe pas très souvent, mais ça m'arrive quand même.
Bah, il fallait me répondre ça.
C'est vrai, non, il fallait quoi?
Voilà, elle n'a pas, bien, pas bien répondu du coup.
Une question. Hein.
Je te le dis facilement parce que je me suis posé la question en fait quand j'avais relu ce chapitre moi-même. Donc je me suis dit, tiens, crash Sophie. J'ai compris ça.
En fait, je vais te dire, je me suis posé la question tout à l'heure à midi en relisant une deuxième fois, enfin en relisant encore le manuscrit.
Voilà.
Bon, alors je fais en français. Bon, alors, là, en fait, le jury, on a beaucoup discuté de vos résultats très intéressants. Donc, premièrement, votre présentation. Alors, unanimement, tout le monde a trouvé la présentation très bien faite. Vous vous êtes très bien débrouillé. Vraiment, au niveau des présentations, vous avez des qualités à l'oral qui sont à noter. Les questions aussi, vous vous êtes très bien débrouillé dans les réponses à des questions qui étaient souvent un peu, bon, quand même pointues, un peu délicates. Alors, le document, particulièrement, alors, franchement, je crois qu'on a finalement de le publier comme ça. Peut-être si vous trouvez des typos, mais enfin, là encore, c'est pas très important. Visiblement, il y a un énorme contenu parce que il y a beaucoup de choses dedans. C'est très dense parce qu'évidemment, il y a ça fait appel à l'état du côté de la physique. Et bon, franchement, c'est un bel effort et ça peut servir d'ailleurs d'introduction vraiment sur la physique et la physico-chimie, enfin, plus les aspects physiques, mais aussi beaucoup d'aspects chimiques du milieu interstellaire. Donc vraiment bravo pour ce document. Alors, sinon, le travail, bon, tout le monde a dit hein, que c'est un pas en avant, que bon, il y a quelque chose là avec ces façons de comparer maintenant aux observations qui ouvrent des portes, en fait, qui sont des... Et donc, d'avoir réussi, d'avoir fait des outils pour arriver, notamment le VSS, etc., développer ces outils, essayer de faire des méthodes rapides pour analyser ces résultats. Et donc, tout ça est très apprécié par l'ensemble des membres du jury. Et ma foi, pour tout ça, eh bien, nous sommes très contents de vous décerner le titre, pas que je me trompe, de docteur en astronomie et astrophysique de l'Université Paris Sciences et Lettres. Voilà, et félicitations, Elena, encore une fois, pour ces accomplissements et cette thèse. Voilà. Merci.
Merci, et merci à vous d'avoir accepté, et tout le reste des membres du jury, pour avoir accepté de relire mon manuscrit, de me poser des questions cet après-midi en plus pour tout ça. Merci à mes directeurs de thèse, il y en a beaucoup, pour tout, pour s'occuper Michel de la salle, de m'avoir toujours suivi, même si des fois à 2 ans, etc. Merci Patrick, même si les échanges n'ont pas été tout le temps super constantes, etc. À chaque fois, ça m'a fait beaucoup du bien et ça m'a ouvert l'esprit aussi de côté scientifique. Et merci à Benjamin pour ces 3 ans et demi. Ça n'a pas été tout le temps facile, en plus avec certaines difficultés que des fois j'ai en certains trucs. Donc, merci beaucoup. Et puisqu'il n'y a pas de peau, du coup, j'ai un tout petit peu d'alcool pour vous ramener à la maison comme petit souvenir, voilà, de cette journée, de ces 3 ans et demi. Merci beaucoup et merci au public du coup d'avoir suivi cette magnifique présentation et les questions.
Bravo, Elena.
Alors,
Merci.
Oui, je parle assez fort, c'est pour ça qu'il faut un amplificateur. Merci beaucoup.
Est-ce que quelqu'un a un stylo qui marche? Parce que je me suis retrouvée avec des problèmes de stylo, ça m'a énervé.
Alors nous, comment on fait pour le champagne?
Parce que attention, je vous lâche pas.
Bon, merci à vous. Je vous remets du son.
Moi, je me suis fait un petit thé.
Ouais.
Moi, j'ai du chocolat italien. De la région d'Elena, en effet. J'ai du chocolat de la bonne région italienne pour le chocolat.
Oh, bah, tant mieux pour toi.